lecture. Okay, so announcement. Midterm number 2 is going to be posted at 5 p.m. I will try my best. I'm still thinking about questions. I want to be a little bit harder because it's take home. But it's not easy to make every question harder. So I will try. Say if you don't see anything at 5 p.m., don't be surprised. But I don't see that would surpass 6 p.m. So I will send a message when the midterm number 2 got posted. Okay, the due time would be next Tuesday, April 5th, not April 7th. I just make it wrong. April 5th, next Tuesday, before class. Okay, so any question again about midterm number 2? It's going to be up to LRT, the same thing as other years. No, April 5th, not April 7th. It's my typo. Okay, next Tuesday, April 5th. Okay, good. So it's the same range as LRT is. So I have to tell you, you won't get much of a hint. Okay, so for example, if I say some function, would that be a quadratic function, increasing function? Wait. I'm confused. Okay, hold on. Let me check the calendar. hold on. April is a Sunday? Oh, geez. I look at May. Oh, sorry. Yeah, April 7th. Okay, it's not good start of the class, right? April 7th. Yeah, I look at May 5th, the Tuesday. Okay, it's April already. So about that, April 7th. Okay. Good. Okay. So I would not necessarily told you some functions quadratic function or increasing function, decreasing function. If in some case you do need to know what a function is, you can Google it, okay, or you can actually draw a function using R, any function of that. Okay, I won't tell you much of detail, much of hints like the past exams. I will told you that function is quadratic function. So for you find your lambda x smaller than c, equivalently is going to be t bigger than c star or c2 star is. So I won't tell you that. I won't tell you that. So you have to find a way to realize what a function is. Okay, so if there's no question on midterm number 2, I will say good luck. Okay, so last time because of fuzzy internet connection, so we end up lose about like 5 to 7 minutes talking about UMP test. Okay, so I wanna talk about it right here again. So let me point a bit bigger. Okay, so pretty much the same thing as we are trying to find the best minimum unbiased estimators. In the testing, you could basically proposing any kinds of testing decision rule. Pretty much like you make a decision to what you want to eat for lunch. You could make different choices, right? You could make different decisions. Some decisions smarter, some decisions more stupid in some sense. So the same thing to our world as well. After we collecting data x1 to xn, we are making decisions. Okay, so decision number 1 and decision number 2. Then eventually you want to see whether or not any decision is most powerful. Any decision is the best decision. So then as a frequentist approach, we make up some kind of criteria, okay, either in bigger class or smaller class. By any means is we have some criteria to talk about how good of a testing is, okay, how good of your test is. So that criteria would be so-called power, okay. So if in terms of power, then we are trying to looking for what? The uniformly most powerful test. Then the uniformly means what? Means uniformly over theta. That testing is going to be most powerful test. Okay. So one famous lemma in 1933 is what? So-called UMP level alpha test, Lehman-Pearson lemma. The definition of Lehman-Pearson lemma is using 2 likelihoods, okay? And then, but testing only about, again, I want to emphasize here is only simple versus simple, okay? Which means that it's your null hypothesis have a single point, theta 0, and then your alternative also have a single point, theta 1. Okay, so then the Lehman-Pearson lemma's rejection region right here, okay, it's a ratio of 2 likelihoods or ratio of 2 joint PDF. One is based on theta 1, which happened in the alternative space. The denominator is theta 0, which under null space. Okay, again, I want to mention it's not surprising this guy bigger than C. Okay, bigger than C means what? That means as long as the ratio bigger than C, I'm going to reject the null hypothesis. Okay, then why it making sense then? Because if this guy bigger than some kind of C, then this guy is bigger than this guy in some sense. Okay, this guy bigger than this guy means what? Your likelihood of your theta in the alternative space is bigger than likelihood of your theta under null space. Okay, of course, you will prefer something having higher likelihoods. Okay, that's the reason why bigger than C making sense. That means up to some level, if my likelihood of null alternative hypothesis is going to be bigger than null hypothesis, then I'm going to reject the null hypothesis, support my alternative hypothesis. Okay, of course, acceptance area would be smaller than C. Okay, again, do I tell? Okay, can it be equal to C? We'll talk about it later on. You will see that original null hypothesis about Lehman-Pearson lemma is there's no equation anywhere. Okay, and it's not surprised to see this if you imagine. Okay, if you imagine what your PDF would be, if X is continuous variable equal than C, basically probability 0. We'll talk about that later on. But what happened to C if actually have that C, if you have that equation, for example, if your X is discrete, then your ratio might actually equal to C. But in that case, what would you do? Okay, good. Okay, then again, the same thing as the LRT. It's, do I told you what is C is? No, I don't told you. I did not tell about what C is. Then how do I find C then? Using type 1 error probability, using size of alpha, you are going to find that cut of C. Okay, good. Again, Please don't mind, I keep saying this. I say last time again as well. Normal definition of the alpha is supremum or supremum theta in theta 0. Okay, but right now your null space theta 0 right here only is what? Single point. So because your null space only have a single point, you don't have to write supremum. You just write your theta is under theta naught. Okay, good. Okay, thanks. Yeah, good. Okay, so then how do I show that then? It's actually not that difficult. As you can imagine, this is 1933 theory. Okay, good. So if you do have this guy right here told you that this testing is size alpha test. Keep that in mind. Okay. So the theory told you that is if you do your rejection region like that way, then any such test, which is size alpha test right here, is going to be more powerful than any level alpha test. Okay. So that means UMP test. Okay. Of course, size alpha test, also level alpha test as well. Okay, good. Okay, sorry. Then B its uniqueness. We are not necessarily show that right here, but just keep in mind it's unique. How do we show that? So if I do think you're more powerful in terms of power function under alternative space, okay, beta theta 1. Okay, if I can given any level alpha test, delta star, if you are trying to claim that test, if I try to claim the testing criteria under Riemann-Pearson lemma would be UMP test, which means that it's more powerful than other level alpha tests. That means I should be able to show that it's the power based on Riemann-Pearson lemma minus any level alpha test power is going to be bigger than equal to 0. Okay. So that means using Riemann-Pearson lemma to construct a test, the power is going to be no less than any level alpha test would be. Okay, so the proof is actually not that difficult. Number one is you need to show that this inequality always holds. Okay, why that inequality always holds? Remember, delta x is test region, is a test criteria. It's actually a binary, right? 1 or 0. If you reject, delta x is 1. If you do not reject, delta x is 0. The same thing is you also having that delta x, another criteria, also is that 1 or 0. Both are binary indicators depending on your criteria. Okay. So imagine the first term right here. Okay. Say if delta x is 1, delta x is 1 as well. This guy basically is 0. Okay. If that guy is 0, then no matter what this guy is, this guy always holds. Making sense? Okay. The same thing goes to what? Delta x 0, delta star x also 0, right? 0 minus 0 still 0. So the first term again equals to 0. So you don't have to worry about what term is. Okay. So it's more discussion would happen to what? Would happen to what if delta x is 1, but delta star is 0 then? Okay, So if that's the case, the first term is positive, right? Equals to 1. Equals to 1. Positive. Okay? How about second term then? Okay. Whenever delta x is 1, that means by Riemann-Pearson lemma is what? If delta x 1, that basically told me that it's lambda x given f of x given theta 1 is bigger than c times f of x bigger than 0. Right? Okay? So that means going back to this. I just pull, yeah. Do you see that right here? Okay? The f of x1 given theta 1 minus c times f of x given theta is what? Positive. Okay? So that make this guy is positive or bigger or equal to 0. Okay? Good. And then what if delta x is 0, but delta star x is 1 then? In this case, 0 minus 1 is negative 1. Is negative 1. This guy right here is negative 1 smaller than 0. Okay? Then what happened to this term right here? The same thing. Because delta x is 0, this guy is my acceptance region, which means that it's what? Means that it's f of x given theta 0 is going to be smaller than f of x given theta 1. F of x given theta 1 smaller than c times f of x given theta 0. Of course, make this guy is what? Negative. Negative. Okay? So that means this guy negative, negative, negative become positive. This guy negative, negative, negative become positive. That guy still holds. So it means by any combination of delta and delta star, that inequality always hold. Okay? If that inequality always hold, how does that help us prove then? Okay? You can actually take integral on both ends. You take integral over what simple spaces. Okay? If you do so, see right here, if you take integral delta x times PDF of x, PDF of x, given theta 1, and then dx. What does this guy mean right here? Some random variable times the PDF means what? And taking integral means what? Nothing but expectation of delta x, isn't it? Given that the true theta is theta 1. And then what is it? What is it? If you go to definition of beta theta, it's in the very beginning of the definition of beta is right here. See? This guy nothing but what? Your power function. Okay? So that means this guy, nothing but my power function. It's okay. That's the reason why this guy is a beta theta 1. The same thing, if you take integral on this guy right here, right? Delta x times minus c, delta x times minus c, fx given theta 0. Then it'll become c times your power function under theta 0. Okay, likewise, integral delta star x, integral delta star x times f of x given theta 1, then become this. Okay, and then again it's integral minus delta star minus c f of x given theta 0 will become plus c power function beta star theta 0. Then integral over 0 is still 0, so bigger than theta 0 doesn't still holds. Okay. So right here, okay, right here, hopefully I did not taking out things too quick. Okay, so by integrating on both sides, I create another inequality right here. And then you move things around. That means you keep beta theta 1 minus beta star theta 1 is right here. And then you move this guy and this guy to the right-hand side right here. Okay, that become b equal to c times beta theta 0 minus beta star theta 0. And then since I said that test is a size alpha test, okay, size alpha test right here, right? The Riemann-Pearson lemma size alpha test. So if it's size alpha test, then beta theta naught under null hypothesis equals to alpha. Now I also told you beta star is a label alpha test. So that means your beta star theta naught is going to be smaller than alpha. If that's the case, then this guy right here is what? Nothing but positive, nothing but b equals to 0. They're making a whole thing right here equal to 0. Then you have that satisfy your current limits. You basically show that it's beta theta 1 is bigger than beta star theta 1. It's exactly what you are trying to show that right here. Okay, so that means indeed using the criteria proposed by Riemann-Pearson lemma could give us a uniformly most powerful level alpha test is the UMP level alpha test. Okay, good. So if I look at example right here, okay. So how do we use Riemann-Pearson lemma to find test then? Okay, that basically only thing you need to work with what backward function. Okay, so right here I do have x1 dot to xn. In the example is what normal theta 1. Okay, so I'm testing null hypothesis is theta 0, and then versus alternative hypothesis theta equals theta 1. Okay, good. And then first thing is you identify this guy is simple. This guy also simple as well. And then if you show a testing is simple versus simple, and then I'm asking if I asking you to find UMP level alpha test. got to know that you are going to use in Levan Pearson lemma. Okay, that's I told you last time. I hate to tell you this kind of pattern recognition idea about using statistics. Okay, but well, that's the reality. So then you do need to identify what's your hypothesis testing is. If you see simple, what's the simple? How do I find UMP Levava test using Levan Pearson lemma? Okay, I will keep reminding you that throughout the semester. Okay, then what does the Levan Pearson lemma told me that is then? So rejection region is I have collecting of data. Then the likelihood function under theta 1 compared to likelihood function under theta 0 is going to be what? Bigger than some cutoff, bigger than C. Okay? Then that means what is the likelihood function is then in this case? Okay, so let me put vector form right here. Okay, so right here it's product of the normal 0, 1, the normal theta 1. That means 1 over square root 2 pi. Sigma square is 1. I don't rewrite that. Then exponential, then minus 2 sigma square. Sigma square 1 again. I don't rewrite it. Then xi minus theta, then taking square. That's my joint PDF, and that's my likelihood function under normal theta 1. Okay, then you're working on a ratio. Okay, good. So exactly what the Levan Pearson lemma told you. Using likelihood ratio. Okay, then right here, I'm going to jump because I think you have been seeing that many of times already. Okay, consecutive product, and then exponential 2 summation I from 1 to n, then xi. One guy is conditional on theta 1 right here. So that means this guy theta 1 is replacing what theta 1 is. Okay, then the other one 1 over square 2 pi, then n, then exponential minus 2 summation I from 1 to n, then xi minus theta 0 taking square right here. Theta 0 right there. Okay, good. So then you're looking for simplification, cancel out. Then exponential right here, you are looking for what? You are looking for cancel out a bunch of things as well. So what kind of things could you save then? So I want to working on the side right here. So in this guy definitely 1 over 2, and then imagine the numerator is what? Xi squared minus 2 summation xi theta xi squared minus 2 theta 1 xi, then plus n theta 1 square. Xi squared minus 2 theta 1 xi, then plus theta 1 square, then put summation, it's going to become less. And then likewise, summation xi minus theta 0 square, again will become xi square minus 2 summation xi theta 0 plus n theta 0 square. Okay, so that means if you take that ratio right here, inside exponential become minus, and then you will see this guy cancel out, this guy not necessarily cancel out, but eventually it could becomes, okay, try to be careful, -2 summation xi, then theta 1 minus theta 0. Yep, I think so. Then plus n theta 1 square minus theta 0 square. Okay. Right here. Okay. So that means, again, I'm going to using similar techniques in the LRT because the Demon-Pearson lemma told me that the ratio of two likelihood function or ratio of two joint PDF, if that's bigger than C, I'm going to reject it. Okay? Then right now it's the whole thing right here as a ratio bigger than C, I'm going to reject it. Okay? So that means, again, it's if eventually I'm going to find C, right? Alpha equals to probability. I don't want not supremo right here because I say multiple times already. Okay, I could put theta right here, and imagine this: if the whole left-hand side is T statistics right here, okay. If Demon-Pearson lemma told me that T got to be bigger than C, and I'm going to using that alpha, I'm using alpha to find cutoff C right here. Okay, good. And then you do need to know what T follows as a distribution. And look at the whole T right here. It's actually the same thing as the laboratory test, right? I mean, same thing, not identical. That means you will see that in LRT as well, the distribution of T statistics may be very complicated. You don't know what that is. Instead, what would you do? You are going to find equivalent region. Okay, I'm going to find really easy statistic called T star right here. Okay, this T star is easy statistics for you to handle. Okay, and then bigger or smaller than C star right here. Okay, I'm trying to find that equivalence to find whether or not bigger or smaller. Okay, I don't know about the direction. I'm going to draw a graph to figure it out. Okay, right here is T is what? Exponential, then minus half. I want to write that so I want to write it more clearly so you will see what happens. Okay, I'm going to take minus half times -2, then become, summation xi, then times theta 1 minus theta 0. Okay, then minus half times plus, then minus half, and theta 1 square minus theta 0 square. Okay, so there's a simplified version of the ratio up to PDF. Okay, then I forgot to mention one thing. It's right here. It's in the beginning. I say simple versus simple, theta 0, theta 1. But in the question itself, I do say theta 1 got to bigger than, I mean, I'm saying got to, it's basically assuming theta 1 bigger than theta 0. Okay, that's very critical because we are going to using that ratio t right here. Okay, and then I'm going to find easy statistic right here. Look at this. Did you see easy statistics? I do. What's that? It's actually summation xi right here. Summation I. Okay, so it's actually same drill as RTS then. I need to evaluate whether or not t is an increasing function or decreasing function or quadratic function to t star summation xi right here. Okay, you need to ask yourself. Again, you will see similar things in meter number 2. You need to ask yourself, is a function is increasing function of summation xi, decreasing function of summation xi, or quadratic function of summation xi? Right here, because theta 1 bigger than theta 0. Theta 1 bigger than theta 0. So that means this guy is what? This guy is positive. Right? Theta 1 bigger than theta 0 is positive. If it's a positive, then I can claim that this is my t star. Then I can claim that this guy is increasing function of summation xi. Okay? Then if this guy is smaller than 0, if theta 1 is smaller than theta 0, then the whole thing right here is what? Negative. Then that will become decreasing function of summation xi then. So, which also told you that it's, you do need to see what value of theta 1 is to evaluate whether or not increasing function or decreasing function of summation xi. Okay, good. So then again, see right here is basically is a cutoff. It's a cutoff of like ratio. I'm sorry. It's a cutoff of a ratio of 2 PDFs, right? That's what Lehman Pearson lemma told me, right? Bigger than C. Okay, so it means this is a critical region, or this is a rejection region based on LR, based on Lehman Pearson lemma. Okay, then I'm trying to find equivalence. This guy, C star. Then if I say that ratio T bigger than C, where that equivalence happens. The equivalence happens in here, right? That means the T star bigger than C star, or specifically it's summation xi bigger than C star. It's equivalent region. Okay, why is that easier for us to handle about cutoff? It's because I can using alpha probability theta naught right here. This is my equivalent region. Then it's so much easier for me to find what C star is. Why? Because I do know summation xi, again, follow distribution, no matter T is. Okay? Or another thing could be done is, if you don't feel comfortable about summation xi, how about x bar? Right? This guy from here to here, n times x bar, C star divided by n. You could write so as well. Okay, then x bar should be easier for you to say what distribution is, right? x1 to xn, normal theta 1, x bar is normal theta, then 1 over n then. Okay, so it means what? That means probability theta naught I can X bar minus 2 theta and not, because theta equals theta naught is your true mean. Okay, so minus theta naught divided by 1 over square root n. Why do I want to do that? I want to standardize. This guy follows z normal 0, 1 x. Okay, so that means you do anything to the left hand side, you do the same thing to the right hand side. Okay, so by doing so, you will know that. Let me take out this. By doing so, you will know that, okay, my z is normal 0, 1. Okay, so this is my cutoff right here, top right here. Okay, bigger is the right hand side probability. Okay, then E equals to alpha, as I claim right here, equals to alpha. That means my cutoff right here is what? Z 1 over alpha. Okay, so that means I can set the whole thing equals to Z 1 over alpha. So I can find what C star is, because divided by 1 root n right here equals to Z minus alpha. That'll give me what? That'll give me C star equals to what? I just what? Move it around. Okay? So I think eventually become what? Theta 0. Then let me see. No, so actually it's n times theta 0, n times theta 0, move, then plus z 1 over alpha times 1 over square root n right here, become your C star. Okay, that means I can eventually write my critical region, okay, based on the Riemann-Pearson lemma is what? Summation xi bigger than n times theta 0 plus 1 over 1 alpha, so 1 over square root n times alpha times z 1 minus alpha. Of course, I can put n in the left hand side, become x bar bigger than theta 0 plus square root n, then z of alpha. It's okay. That's a whole package about using Riemann-Pearson lemma to find your UMP test. It's okay. I want to mention one thing is, see, if you don't know about bigger or smaller, okay, look at what your direction of your alternative hypothesis is. Okay, it making sense, right? Summation xi got to be bigger than something in order for you to reject it, your null hypothesis. If you truly think your alternative theta, as a theta 1, is bigger than theta 0. Okay, good. Any question on this? I want to stop a little bit for you to take a note or anything. You could finish that. Okay. So I do see that lagging things about my Apple Pencil on the monitor. So if you cannot follow my speed, then let me know. Okay. So, well, I posted that every time on the YouTube. So you can also go back to YouTube. Okay. Okay. Let me move on to right here. Okay, good. Another point I really want to make is right here. Okay, so, okay, I maybe want to make a bigger bit right here. Okay, so see right here. I'm trying to cover this point. Okay, our hypothesis using Riemann-Pearson lemma. This is my rejection region. Okay, let me ask you one thing. Did you see theta 1 anywhere in your rejection region? The answer is no, right? And it making totally sense, like I keep telling you, it's in the frequentist thinking, we always protecting null hypothesis. We don't really care about alternative heads in our criteria. Okay, so of course you won't see any information or any like a hint about alternative hypothesis in your critical region. That also means that, imagine this, if you are doing testing, it's actually simple in the null hypothesis versus composite in the way of theta bigger than theta 0. Okay, if you actually do that, imagine this. Imagine every theta 1. Okay, imagine every theta, or say imagine every theta in your alternative. Imagine there are bunch of theta 1 is in your null hypothesis, in your alternative hypothesis. I'm going to say again. Imagine a bunch of theta 1 in your alternative hypothesis. For that each theta 1, what rejection region you are going to use would be the same as this guy right here under Riemann-Pearson lemma. Okay? Because this guy right here doesn't care about what your theta 1 is. For example, let me take, for example, maybe I cannot see your eyes. I don't know if you understand that or not. Say if theta is theta equals 0, for example, versus null hypothesis, if simple versus simple, okay, null hypothesis theta is 0, alternative theta is 1. If simple versus simple, right, by Riemann-Pearson lemma, you got this rejection region. Okay, of course, you're replacing theta 0. You're replacing theta 0 as 0. Okay, good. And then imagine your alternative theta is 2. Okay, if you working on this hypothesis testing, you will get the same UMP test here. Because again, Riemann-Pearson lemma don't care about what theta 1 is. Okay, so that means if we are doing testing about composite theta bigger than theta 0, that means you have 1, 2, 3, a lot of points right here, all using the same test region. Every one of them is UMP test. So that means it's as long as, even though your Riemann-Pearson lemma help you to find UMP test under simple versus simple, the same test region also apply to simple versus composite. That means as long as your testing is simple versus composite, how do you find UMP test? Still using Riemann-Pearson lemma. Okay, that's what I want to say. It's okay. Again, pattern recognition, simple versus simple using Riemann-Pearson lemma, simple versus composite also use Riemann-Pearson lemma. Okay, then this slide is exactly answering the question about what happened. Yeah, okay, so Owen asking about what if theta 1, right? So right here, I'll take this out. Okay, good. So what if theta 1 is theta smaller than theta 0 then? Okay. Again, it's, you can imagine I can get in really easy testing is theta 1, theta equals to theta 1 smaller than theta 0. I could do that, right? So not asking about this. I can get started from easy testing, simple versus simple right here. But my theta 1 is smaller than theta 0. Okay, so by simple versus simple, I can using Diemann Pearson lemma, NP lemma, like using Diemann Pearson lemma to give me a UMP test. Okay, and then you go through everything right here. Okay, everything goes right here in the left hand side panel it, but I do not answer already, which will give you this. Your region eventually become x bar smaller than theta 0 minus 1 over n z alpha h. Okay, by using that simple versus simple, give you easy test region using Diemann Pearson lemma. And then imagine that it's your theta 1 in a space of less than theta 0, you can have a bunch of points. That bunch of points all using the same critical region by Diemann Pearson lemma. So that means the same test region is going to be UMP test for your eventually testing of alternative theta smaller than theta 0. Making sense? Owen?
Yeah, makes sense. So if it's like theta not equal to 0 or not equal to theta 0, we need to use this twice to find the rejection region, right?
Why do you need to use twice then?
Because
so you are thinking it's alternative right here. Theta
not equal to theta 0.
You said yes?
Yeah.
Okay. No?
No. Oh, so.
But yeah, thank you for mentioning on that. So I should say more specifically, I apologize. I say simple versus simple actually composite right here. Composite right here. Only one-sided. Okay? So later on, we'll talk about it. This guy, if you do have simple versus alternative composite, but if it's two-sided, you don't have equation right here. Okay, you do have if you don't equal to theta 0, this guy right here don't have a UMP test.
Oh, okay.
Right. No UMP test. Okay. I'll talk about that, why that guy doesn't have UMP test. Okay. Good, but you do remind me one thing is I do need to emphasize, even though simple versus simple Diemann Pearson lemma, simple versus composite also Diemann Pearson lemma, but this guy alternative right here got to be one-sided. Okay? Again, it's the same thing happen right here is what? The sign of the UMP test is the same as alternative. Okay? So again, if you don't know about which sign that is, then follow the alternative. Okay, but through that solid derivation, you will see that it's less than. It's about less than. Okay, good. So right here, so original Diemann Pearson lemma doesn't talk about what to do if you do have equation. If you do equal to C, okay, so original Diemann Pearson lemma doesn't give you any recommendation about what C is. But the point is, if C is continuous, right? If C is continuous, the probability of ratio of two continuous random variables is 0. What's the probability? So you don't need to worry about equation things. It doesn't matter if you have x continuous. Okay. But sorry. But if x is actually discrete, then equation right here might happen. Okay, you do have you may not have positive probability, right? You may say if you may, what happens? If you does have the positive probabilities, right? They might also doesn't say how to do that. But the point is, you can actually adjust your alpha to avoid that cutoff C. Okay, which means that is just avoid using that cutoff to do your testing. You could choose another cutoff, which basically would avoid equations, and then at best you adjust for your alpha. Okay, you could choose in different C or choosing different alpha is equivalently. You choosing different alpha, then you choose a different cutoff to avoid that kind of testing, to avoid that kind of equation things. Okay, good. Means that it's just simply using avoid, okay, using that value of C. Okay, that could also mean that is you choosing different value of cutoff, and then you choosing different value of your type 1 error. Okay, again, in summarize, simple versus simple, Riemann-Pearson lemma, simple versus composite, one-sided, very important. Okay, also Riemann-Pearson lemma as well to find UMP test. Before I'm going to move that to composite versus composite right here. Say if you do have composite versus composite, but still also one-sided, how would you do? Okay, before doing that, before using any theory to talk about it, I want introducing one property which is quite important to a testing called monotone likelihood ratio. Okay, so some likelihood itself is actually, more properly regulate. By saying so means that is that likelihood function is prettier than other likelihood function is. Okay, so one MLR property is defined as follows. So say if you do ratio to PDF, okay, under theta 1, under theta 2, under theta 2, under theta 1, you have a ratio of 2 PDF, okay? That ratio of 2 PDF would depending on X only through TX. That means the ratio is a function of some statistics, okay? So if that's a monotone increasing function of that TX for every theta bigger than, for every theta 2 bigger than theta 1, okay? If there's a such function, if there's a such likelihood function, or saying if there's such joint PDF, then we'll call this kind of likelihood function having that properties of monotone likelihood ratio property. For example, Poisson, right here. Okay, say if x1 to xn is Poisson, and then you're working on a 2 joint PDF. Okay, for example, I can working on right here, but I do need to save this, and then I do create another panel. Then I'm trying to say, okay, I can write something on it. So say if x1 to xn is Poisson, so I can save something, right? Okay. Your side would be BIOS. Okay. So if I do have Poisson theta right here, focus theta bigger than 0. Okay. And how do I show Poisson have this kind of monotone like ratio property then? Easy. Say if you have joint PDF, 1 under theta 2, and then 1 under theta 1. So eventually you are trying to show this guy increasing function of state of TX, of some TX, of some TX. Okay. And then if theta 2 bigger than theta 1. Okay. So then just working on that. Join Nyquist function, right? So just pull out. Okay. Join PF. Then Poisson theta would be xi factorial lambda xi e minus lambda. Lambda right now becomes theta 2, theta 2. And then over n, you do have xi factorial, then theta 1 xi, then exponential minus theta 1. Okay? Based on different value of thetas. Okay, as you can imagine, I want to jump a little bit, so I could see somehow cancel out. So eventually I could write as what? Theta 2 summation xi e theta n theta 2x. Then theta 1 summation xi, then e minus n theta 1x. You know, this part of xi cancel out. Okay, so writing that down as what we have in the slash right here. Okay, basically means that I taking exponential, they're taking log. If I taking log, summation xi coming down, then log theta 2 minus log theta 1. Okay, then minus n theta 2, then plus n theta 1 is right here. Okay, because log 2 minus log 1, I can purpose write that 2 log theta 2 divided by theta 1. It's theta 2 divided by theta 1. It's okay. This guy is not really critical, so I just leave it there. Although I can combine of the n, I can take out n and become theta 1 minus theta 2 as well. Okay, so the goal is you are trying to find the ratio of the Poisson's PDF. Say that's increasing function of some TX right here. Okay, then if I choosing summation xi as that TX, okay, how do I know this guy right here is an increasing function of summation xi then? Okay, really depending on this side right here. If this side positive, then increasing function of summation xi. If that side negative, then decreasing function of summation xi. Making sense? Okay, then does this guy positive or negative? The answer is positive. Why? Because I say if theta 2 bigger than theta 1. Because theta 2 bigger than theta 1, this guy right here, the inside guy bigger than 1, taking log become positive. So it means by this evaluation, I do know that guy is positive. Okay, so that I could say that it's the ratio is increasing function of the summation xi. So Poisson does have that monotone like ratio property. Okay, good. Then this slide actually having is what? So in the Kunzelberger, the MLR property will be defined on the distribution of the TX directly. Okay, so there are different definition. Both definition will work. Okay, then the one would be it's say so right here it's definition of Poisson x1 definition of the PDF on individual one x1 to xn follow Poisson. Then this theory definition of MLR in Kunzelberger actually talking about different distribution of TX, for example, distribution of summation xi right here. Okay, so that means using definition in Kunzelberger, you're deriving your PDF right here using the PDF of summation xi's. Okay, so let me say it again. The showing right here is based on single random variables PDF. Okay, then in Kunzelberger, they are using the PDF of the TX. Okay, but the showing wise is the same. Well, it's not surprising if you do having that statistics right here is a sufficient statistics. If they are sufficient statistics, then two guys are actually identical. For example, I'm showing ratio of the single PDF joint PDF, right? And then by factorizational theory, I can write the joint PDF into what? GT theta and HX. Then by factorizational theory, we do know TX right here, right? It's sufficient statistics. Okay, then how to make a PDF? Just standardize it. Okay, you will see a bunch of example. You can actually borrow something from HX, putting down anywhere to make that PDF, to make it like TX PDF. Okay, then in that case, then the ratio of individual one is the same thing as the ratio of the distribution of the sufficient statistics. Okay, that's what I meant to say. But again, they are actually identical. So either using single one to check it or using your TX distribution direct to check it. By any means, okay, the reason we want having that is what? I want to introduce so-called Cullen-Rubin theory. Okay, again, pattern recognition. If you do have the testing is what? Composite versus composite, but they are one-sided. One-sided means bigger and then smaller equal to one-sided. Okay, one-sided. If you do see that testing, then how do you find UMP test? Then you're using number one, T sufficient. Okay, if you can if you can find sufficient statistics, and if the PDF has their MLR property, then by Cullen-Rubin theory, we told you that it's using a sufficient statistics bigger than some cutoff is going to give you UMP label alpha test right here. Okay, again, I'm not going to show that why is the UMP test, not like an easy way to show that in the Lehman-Pearson lemma. But again, what I say is what? Follow direction of the alternative hypothesis. Okay, but keep in mind, whenever you see composite versus composite and one-sided, you are thinking about using Cullen-Rubin theory. And then using Cullen-Rubin theory, you got to do two things. One thing, show that T is sufficient. The other thing is show that PDF having the MLR property. Okay, good. Then only 5 minutes to go, so hang there. Okay, so if I switch so-called reverse problem, which means that it's I switch side, right? This guy is smaller than, bigger than. If I switch it to null hypothesis bigger, alternate hypothesis smaller, then how do I find UMP test? Again, just follow the side of a UMP test. Okay, so if that switch also happens, if that switch, the Kahn-Rubin theory is also can also be applied. Okay, good. But again, it's you need to choose inside, follow the alternative hypothesis. Okay, so we kept saying that it's always bigger than C or smaller than T0 things. Again, I don't told you what it says. Then how do we choosing C or T0? We kept saying so multiple times. How to decide it? Again, using type 1 arrow to decide that. Using type 1 arrow to find your cutoff. C right here. But right now your null hypothesis, your null space is no longer single points like Lehman-Pearson lemma. Your hypothesis is having multiple points, theta smaller than theta 0. So that means you do need to find which theta is going to maximize whole probability. Okay, to talk about the supremum of the probability equals to alpha x. Okay. One more thing I want to mention is you shouldn't feel surprised. Oops. Surprise. Okay. What I mean to say is, if you do find out this probability and you talk about whether or not the probability is increasing function or decreasing function of theta, okay, don't feel surprised. Good things always happen in what? In the boundary. Okay, I think 99%. It's again, I cannot rule out 1%. Could be possible, but yeah, I cannot think of any particular example. It's not happening in the boundary. Okay, but of course you need to talk about it. You need to talk about saying the probabilities increasing function of theta. In this case, okay, or decreasing function of theta in this case. Okay, such that the supremum is going to happen in the boundary. But it would be not a surprise if you find out your theta equal theta 0 is going to be to maximize the type 1 error probability. Okay, only 2 minutes left. I can't tell much about this. I can talk about it next Tuesday. Okay, again, summarize simple versus simple, simple versus composite, one-sided, using what? Lehman-Pearson lemma to find UMP test. You do have composite versus composite. Both are one-sided. Using what theory? Kahn-Rubin theory to find a UMP test. Okay? It turns out to be if you do have a simple versus composite right here, you don't have no UMP test. Okay? I cannot show you specifically about why there's no UMP test. Okay? But I could actually told you that if you do find this kind of simple versus composite, okay, you might end up likely you do have your power function like this. Is alpha like this. Okay. You end up finding some test having good power function like this. Okay. And then you will end up with some lousy testing is going to be more powerful than that two-sided test at some point. It's 1:45 right now. I cannot bring a detail. I would told you what that is on Tuesday, why you don't have UMP test in this kind of simple versus composite situation. Okay, any question? If not, we are going to dismiss the class. Okay, if you do have questions, you are more than welcome to stay. I'm